A small update. You cannot put it all in the same bag. You cannot say that all of them are the same. Okay? What I mean by that? It's very simple. You have, as an example, you have a cross-plane crankshaft from a V8, from the 157 over there. Okay? That the journals, they're 90 degrees apart. Okay, I don't have to do all these things. If I had the machine to put the bob weight, to get the weight from the piston connectors and to put it on, put the clutch back and the damper pulley and then spin it, and then to see if it's balanced the crankshaft, you're gonna see that it's gonna be all over the place. So I don't have to do all these things. All right? Okay, never mind. So V8, 90 degrees configuration, the cross-plane crankshaft, it's 90 degrees, the journals apart. Okay, 101. A 4-cylinder inline 4, okay, it's 180 degrees apart because a flat plane, 1342, classic, okay, it's 180 degrees apart. That's why I need the balance shafts, you know, for the middle range RPMs, because it's unsteady and then it comes nice on the higher RPMs and it's beautiful. On the inline 6, it's 120 degrees apart, the crankshaft. On the inline 6, okay? So you cannot compare the V8 cross-plane crank with the inline 4, 180 degrees, the flat plane, and with the inline 6, the 120 degrees apart. It's wrong. It's not, doesn't apply. It's not the same thing, all right? Why you can rev it so high? Because one of the reasons is this, because of the balancing of the crankshaft. I'm gonna give you one. Let me say something. We have a stock stroke on this crank. All right, that this is 86 millimeters, if I remember right. On the specific one, it's 86 millimeters. All right, at 9,000 RPMs. At 9,000 RPMs, the 86 millimeter stroke, it's 0.086 meters. Okay. Now, you said in right double M. It's 0.086 meters at 9,000 RPMs, has a piston speed 25.8 meters per second. Okay? That's the piston speed at these RPMs. Fine. If you understand this and what I'm saying, it's gonna make sense what you see on the bearings. Okay? In any case, let's continue. Let me write now down. I'm gonna write some numbers. Rev limiter, okay? Rev limit, 9,000 RPMs. This what I'm writing now, it's existing, this car, okay? And I have worked actually on this car before. It's been now more than 20 years, but I have worked on these cars before, okay? Rev limit, 9,000 RPMs. Piston speed, 23.2 meters per second. You see? Why? Because the stroke, it's 77.4 millimeters. That's why it's 23.2 meters per second at 9,000 RPMs. Why? It's dual overhead cam, and for what I'm talking about the B16B, Honda Civic Type R. 99, 2000 model year. We have in Greece plenty. We had. I don't know now if it's existing. Inline 4. All right. So in this case, it's different crankshaft. It's flat plane crank. You have 77.4 millimeter stroke, and you have at 9,000 RPMs 23.2 meters per second. When here in this case you have 86 millimeters stroke. Okay. At 9,000 RPMs, and you have 25.8 meters per second. Here in this world, the mass, when you rotate something, when you speed up something, it's like, how to explain now that? If you put an apple on a net and you start spinning it, if you spin it fast enough, it's gonna explode. The same principle, it's also for the rotating assembly, for the pistons and the connecting rods and all these things. It's the same thing. You're gonna reach at one point that you're gonna start deform, okay? And the next step is gonna be explosion. you're gonna come apart. That's exactly what's applied here. It's not my rules, it's not my laws, you know, it's for this world. Once again. That's why I'm saying that with a billet steel connecting rods, it's gonna be much better. Now you're gonna have much more mass at 9,000 RPMs. Yeah, you might not need to rev so high for safety because you're gonna explode. Yeah, but it's not gonna deform. It's not gonna be that soft. So you have to balance it. You have to find the sweet spot. But in any case, that's not my call. That's not my call. Just to answer, okay? Now, like I said also before, this going at the machine shop. I wanna see this crack. I wanna check now this stupid crack. What's going on? How deep it goes? It goes to the threads. We're gonna have a problem here. What in hell is going on here? Okay, it's far away from the cylinder, but it's not good to have these kind of things. In a cast iron, guess what? It's not gonna stop there. It's gonna continue. You have thermal expansion, you have vibrations, you have pressures. It's not gonna stay there. From the other hand, you know, I can say to my friend, you know what? Bring me on stock block to be nice and healthy, and put it on. The thing is that after that, what it takes, we need to machine the crankshaft bearing caps to remove, let us say, 0.25 or half millimeter, and then make again the main line, machine the main line. Because these are the billet caps, it's not the stock one, the cast one. The cast one, it might crack. Yeah. Okay, that's it. Small update. I hope that you understand. I hope that I make myself clear. If not, I'm sorry. Move on. Thank you. Over and out.